Hello and welcome to the pre-lab video series for York College of Pennsylvania's General Chemistry 1 sequence. This video or screencast will provide you with information for the acid-base titrations experiment, part of the Chemistry 1 laboratory curriculum. So the acid-base titrations experiment has actually two primary goals in mind. First, we're going to use titration to prepare and standardize a solution of sodium hydroxide. And then in a second half of the experiment, we'll use that sodium hydroxide, once it's been standardized, to determine the molar mass of benzoic acid. Now, the sodium hydroxide that you make today, you'll keep for at least one other experiment that you'll be performing in the next lab, the neutralizing power of antacids exercise. So you want to make sure that when you're all done, you don't dispose of your sample of sodium hydroxide. That's also an incentive to do a really good job with the standardizing technique in the first half of the lab, since you're going to use this sodium hydroxide in the next experiment, and the outcome of that experiment will in part depend on how well you do today with your standardization. The determination of the molar mass of benzoic acid is a common technique in which we find the molar mass of an unknown compound. Now, in today's or this week's lab, you'll know that it's benzoic acid that you're working with. But imagine if you were working with an unknown material that you identified as having acidic properties. You could use an acid-base titration to get an idea of what that material might be. And so we'll see how a chemist would do that through the second part of our work today. So let's look at some of the key concepts that are going to be involved in today's experiment. You've already done a titration, a redox titration involving bleach and sodium thiosulfate and iodine as the indicator. This titration is a little bit different. It's a 1-to-1 mole ratio, which makes the stoichiometry a lot easier. So at the end point of our titration, which will be visualized by a very light pink color in our solution, perhaps I can fade the color here to give you a nice light pink color here. We're going to know that the moles of acid present in our beaker or our flask will be equal to the moles of base present in that flask. Now, both the acid and the base will be usually in the form of solutions. And a solution, while its concentration can be measured in a number of ways, is usually measured with molarity. And so molarity, of course, is the moles of the solute, the actual acid or base, divided by the volume of the solution. So if we solve this equation for the moles, we would arrive with molarity times volume. And so each side of our shaded equation up here would become the respective molarity of the acid times the volume of acid used, would equal the molarity of the base times the volume of the base used. When one of the terms is an unknown, you can use the other three known values to solve for it. And that's what we'll be doing in the two different parts of our experiment. In the first part of the experiment, we'll be using the, basically we'll know everything about the acid. The acid will be delivered to our solution, to our titration, as a solid. So we'll determine its moles not from molarity times volume, but from stoichiometry by converting literally the grams of acid that we weigh out and add to our flask to moles. The base, on the other hand, will be added to the reaction, to the flask, via the titration in the form of a solution. So it's still appropriate for the base to think of its moles as coming from molarity times the volume. But we don't know the molarity of the base at this point. It's something we'll have just made and not yet calculated. So we can solve this equation, moles of acid equals MbVb, for the unknown molarity of the base. Now you'll want to conduct this titration several times, and in each trial you would add a unique amount of acid, and then you would get a subsequent unique amount or volume of base. And so then you would take the respective moles divided by volume for each trial to calculate a molarity. Titrations can be performed very, very accurately when done carefully, and thus you should be able to get a very consistent result for the molarity of your base. And you're asked at one point during your lab, after you've conducted your 3 titrations, to calculate this molarity during the lab, to not wait until after you're done with lab, in other words, to see how close your 3 values come to one another. We do want them to be very close, and so a small range or error bars have been established. See your lab manual for that specific value. If your values don't fall within that, so your average value, if they don't fall within that, you need to conduct more titrations until you do have a very accurate value for your for the molarity of your base. Again, this is important since we're going to use this base in the next lab as well. So we really want to know what its concentration is. So that's the standardization. That's the first half of our lab. The second half, we can now use this base. Now we know its concentration, and therefore anytime we add a specified volume of that base, we know how many moles of base are present. So if we react that base with an acid that we don't know what it is or how much of it we have, we can use the titration concept to tell us how much acid is present. So we're going to do this with benzoic acid, and because we can look up the formula of benzoic acid in our laboratory manual, or you could find it online anywhere, you'll easily be able to calculate a percent error and decide how accurate this method is. So at the end point of your benzoic acid with sodium hydroxide titration, once again it's true that the moles of benzoic acid are equal to the moles of sodium hydroxide. The base has been delivered by the solution, so its amount is MbVb, but the acid is an unknown. So we're going to leave it as an unknown, but if we take molarity base times volume base, that is moles of base and telling us how many moles of acid are present. So we've solved for how many moles of acid are present, and that's because, again, it's a 1-to-1 ratio in this reaction. Now then, the molar mass of our acid is related to 2 things: the mass of the acid and the moles of the acid. So molar mass is simply the ratio of mass of your sample to moles. You will have weighed the sample out literally before you began the titration, and then you have solved for the moles via the step up above here. And so you simply take your mass from your balance divided by your calculated moles to give you the molar mass of benzoic acid, which you could then again calculate a percent error by comparing it to the known mass, the molar mass of benzoic acid. Okay. You could then do this for any unknown acid to help you identify it. Molar mass is one of the common first things that you try to get when you're identifying an unknown material. Let's briefly look at some of the techniques in the procedure. You should have a fairly recent memory of conducting your titration. So I've pulled out a few pictures from our titration video that was made for the redox titration lab. Again, here's our setup. We're using a burette, the long thin column with a stopcock at the bottom, mounted properly into a burette clamp. That's the clamp with the sort of the springy sides that hold the burette, and the white base, as opposed to a regular ring stand which has the black base. You really should be using one of these larger, more sturdy, wide bases. You might need some flasks and funnel and other paraphernalia. As we scroll through, when you fill the burette, try to fill it with a funnel to avoid spilling. I tend to fill, or recommend that you fill up above the 0 line in your burette, and then you have to run some of your solution down through the tip of the burette. Before you begin any titration, your tip should be filled with your solution. Prior to all of this, of course, we've rinsed out our burette. Remember that that's an important step as well. Okay. Now, When you actually begin to titrate, I recommend that the tip of your burette be below the lip of the flask into which you're titrating, and you want to record the initial volume in your burette, and then you'll titrate to the end point and record the final volume. During this process, you will use an indicator. In this experiment, you'll use an indicator called phenolphthalein, which will be colorless in acidic solutions. Since we'll have acid down in the bottom of our flasks in this experiment, you'll begin with a clear or colorless liquid down here. And as you add the base, you will see pink color show up. The phenolphthalein is a deep pink or purplish color in basic solutions. Now, at first, you'll have a large excess of acid, so the color will not change much at all, and then you will start to see the pink color forming literally where the acid is dropping into the flask. So you'll want to be swirling. This picture is a little blurry because it's captured from the video where I was swirling the titration contents, and this helps promote mixing, of course, of the acid and the base. When it gets harder and harder to make the pink color disappear with swirling, you want to begin to slow down your titration to the point where you are just dripping one drop at a time and allowing yourself enough time to swirl that drop and mix it uniformly throughout the contents of the flask. We're trying to get to the position where we can add one and only one drop, and we see the color change from colorless to a light shade of pink. That would be a careful, well-conducted titration. Okay? And so that's the end point when you achieve that light pink color. If you are dropping too much base in and several drops come in and bring about the pink color, you really haven't performed that titration correctly, and you would need to discard that trial and do another one to replace it until you get 3 good trials of your titration. Okay? Let's look at the pre-lab questions. These calculations in the pre-lab are very important and definitely what you'll be doing as part of the calculations for your lab report. So pre-lab question 1 says we've taken 25 milliliters of a known concentration of hydrochloric acid and neutralized or reacted it exactly with 14.8 milliliters of sodium hydroxide. So that would be the end point of that HCl NaOH titration. What is the concentration of the base? So we would begin with the equation that at that end point the moles of acid present are equal to the moles of base. Since each of these came from a solution, it's appropriate to use MAVA to represent the moles of acid and MBVB to represent the moles of base, the molarity of the base being the unknown quantity. So then we simply would manipulate to solve for the molarity of the base, and we would find that it's about 0.211 molar. Okay? Now, we've used the volumes here of liters. That's the appropriate volume unit for molarity, so make sure you pay attention to that. In the second pre-lab question, this is similar to what you'll be doing in part 1 of your exercise today. You will use what's called potassium acid phthalate. It is an acidic species that will provide the hydrogen to neutralize the hydroxide ion on the base. So you would weigh out a small sample. In this case, we've used 0.172 grams. And we have neutralized or reacted it with 25.3 milliliters of sodium hydroxide. The 30 milliliter number here is really a red herring. It's not used in our calculation at all. It was simply the volume of water we used to dilute the solid acid. Okay? What's really important here is how many moles of potassium acid phthalate were used. And that number does not change with the volume to which we diluted them. So our first part of the solution is to convert grams to moles with the traditional stoichiometry conversion, dividing 1 mole by 204.22. That's the molar mass of potassium hydrogen phthalate. Now these moles of acid are equal to the moles of our sodium hydroxide base. The base was delivered by the titration, and we do know the volume of the base, so we can solve for the molarity of the base. So because the base was a solution, MbVb is appropriate to express its moles. But the acid, again, we already know that number. We don't need to convert that to a concentration, in other words. We already have it. And so we would once again solve for molarity of the base by taking moles of the acid divided by the volume of the base. And we came up with a much smaller molarity here, 0.0333. Okay. Question 3 is very similar to how you will, shows you how you will calculate the molar mass of your benzoic acid. So in this case, it's an unknown organic acid that we're told is titrated with our sodium hydroxide. We weighed the sample of the unknown acid, similarly to how we weighed the potassium acid phthalate up above. But now we don't know the molar mass of our organic acid, so we can't calculate its moles directly as we did with this calculation up here. Okay? So how can we calculate the moles of organic acid? Well, the moles of acid present are equal to the moles of base at the end point of our titration. So the moles of base comes from the molarity of the base times its volume, just as we've done in the 2 previous examples. But we know both of these numbers now, and in your experiment today, after you've standardized your sodium hydroxide, you'll know its molarity, and then you will physically perform a titration to obtain the volumes that you'll use. Once again, notice I've converted milliliters to liters in this so that my units correctly give me how many moles of base are present. Now the moles of base are equal to the moles of the organic acid. So not only do we have 0.00219 moles of sodium hydroxide at the end point of this titration, we have 0.00219 moles of the acid. So lastly, the molar mass of the acid is, as we talked about earlier, the mass of our sample divided by the moles specifically in that sample, which we just found. So we take the weight or mass of our sample, 0.345, divided by the moles that we determined were in that sample, and we get a molar mass of 157. If this was an unknown, we can now compare it to a list, look through the literature for acids that have molar masses around this value, and we could start to narrow down the possibilities. And then we would perhaps have to measure some other physical properties as well to determine the final identity of our unknown acid. Okay? So that wraps up what we need to know for today's experiment. Again, the key concepts are that at each point when you develop the light pink color in your titration, the moles of acid and base are equal to one another, and you can symbolically solve for those moles with a couple of different formulas depending on how you have brought the different materials to that reaction. When they're solids, you would use stoichiometry to calculate the moles. And when they're solutions, you use the relationship between molarity, moles, and volume. So good luck in determining your concentration of your sodium hydroxide. Again, I really want to stress that you get an accurate or as accurate as possible value, since you'll use it next lab in determining the neutralizing power of an acid. And in that lab, your data point will become part of the class collection of data. So your contribution to the class will be very important, since you'll want to be able to contribute accurately to the overall data set that gets generated. Okay? Good luck, and I hope you have an enjoyable time titrating your benzoic acid.